Okay, we are now into section 3.7. This section is called implicit differentiation, and that will become clear as to why we call it implicit differentiation in a bit. The bottom line is it's really just the chain rule, okay? So it sounds like it's something different, but it's actually the chain rule. Now, the reason we use implicit differentiation is when we have what are called implicitly defined curves. So notice this is not in the form of y equals f of x. It's not y equals something that's all x's. That would be a function, and these types of curves you can tell are not functions, right? This would not pass a vertical line test. But these are actually very important curves in practices later, and so we still want to know like what the slope is at any point. When this was first thought of, what people ended up thinking of is let's break this up into pieces that are functions, okay? And then we can take the derivative normally. So you could break this up from like here to over to point A here. That part of it's a function. Then I go from point A to the origin here. That part of it's a function. And then I go from the origin down. And that part of it's a function. So if I could split it up and solve for y on each one of those, then I could just take the derivative normally. But I can't do that, or it's not easy here. I'd have to solve this for y, right? It's not easy to do that. It might not even be possible. Okay, in this case, this one could be solved for y pretty easily, right? I could say y squared equals x. So y equals plus or minus the square root of x. In other words, the positive square root of x would be this guy. Now I have a function. And minus the square root of x would be this guy. So I can think of it as two separate functions. But I think if I think of it as the curve of y squared minus x equals 0, then notice that it's this whole curve. So without having, in this case, it's simple to solve for y, and you can see the two separate functions, but it's still best not to have to do that if we can afford not to. And here's a circle, right? Not a function. Typically what people will do is they'll think of the upper half of the function. So it's solved for y, you get plus or minus the square root of 25 minus x squared. So the positive square root of 25 minus x squared is the upper half of the circle. The negative square root of 25 minus x squared is the lower half of the circle. And so people will break it up that way. But again, we can use implicit differentiation, which you don't know what it is yet, but we can just take the derivative, find dy dx without simplifying these equations, just the whole curve. And that's what implicit differentiation is about. So the way you do that is you leave the equation the way it is. So I would leave each one of these equations the way they are, and I would differentiate both sides of the equation with respect to x. However, every time you come across a y, you have to remember that that itself, if we could solve for y, would be a differentiable function of x. So you have to use the chain rule whenever you come across a y. Just remember that. And then you collect the terms with dy dx on one side of the equation and solve for dy dx. In other words, this step 2 is just algebra. It says treat dy dx as a variable and solve for it. Okay, so that was a longer explanation, but now let me go through this example here. So that first curve, remember this x cubed plus y cubed minus 9xy equals 0 is this guy. So I'm not going to solve for my three different functions of x like I talked about. I'm just going to leave it in that form and find dy dx. Okay, so the first step is to differentiate both sides of the equation with respect to x. So I take the derivative with respect to x of this equals the derivative with respect to x of 0, right? Differentiate both sides with respect to x. So when I differentiate x cubed, that's simple. There's no y's in there, so I just think of that like normally. Take the derivative with respect to x of x cubed, it's the power rule, 3x squared. But now I have y cubed. So I want the derivative with respect to x, but it's y cubed. So I have to think of y as some unknown function of x. So I first take the derivative of the outside, which is 3, times the inside, which is y squared. Because I don't know what y is, I just leave it as y. Then I have to multiply that times the derivative of the inside. My inside function is y, so I don't know what y is, so I just write it as dy dx. Minus 9xy. If I want the derivative of that, I have to think of this as a function minus 9x times another function y. Remember, I don't know what y is. I didn't solve for y, but I have to think of it as a function of x. So minus 9x times y, I would have to use the product rule. So the first, minus 9x, times the derivative of the second was y, so I just write that dy dx because I don't know what y is, plus the second, which is y, times the derivative of the first, which is minus 9, so minus 9y. Equals on the right-hand side, the derivative of 0, the derivative of 0 is 0. And now I have simply, I've done the derivatives, and I need to know that what dy dx is. I need dy dx equals something. So now it just becomes algebra. Put all the terms with dy dx on the left side of the equation, which is the second and third term here, and factor out dy dx. So I get dy dx times 3y squared for this guy, and a minus 9x for this guy. All the terms that don't have dy dx go to the right side. So I bring over the 3x squared as a minus 3x squared. I bring over the minus 9y, and it becomes 9y. Then you simply divide by whatever dy dx is multiplied by, right? Simple algebra. Put it over here. So dy dx is 9y minus 3x squared over 3y squared minus 9x. And that's dy dx. So you don't have it in terms of all function of x because you don't know what y is. You actually get your answer in terms of both y's and x's most of the time when you do implicit differentiation, but that's okay because you'll know the point on the curve, and if you want to know the derivative at a specific point, you just have to plug in both the x and the y value. So that's the process of implicit differentiation. So in part B, if I want to use implicit differentiation to find dy dx, I take the derivative of both sides with respect to x. Again, that's the second curve up in that picture we looked at before. So I get derivative with respect to x of y squared minus x equals derivative with respect to x of 0. So the derivative of y squared, I got to think of y as an unknown function of x, so this is a function of x squared. So I have to take the derivative of the outside, which is 2 times y to the first power, 2y, times the derivative of the inside, which is y. I don't know what y is, so I just write it as dy dx. 2y dy dx. Okay, minus the derivative of x, the derivative of x is just 1, equals the derivative of 0, which is 0. Solve that for dy dx, I get dy dx is 1 over 2y. Okay, part C, we had that circle, right? X squared plus y squared equals 25. If I want to find dy dx, okay, I just take the derivative of both sides with respect to x, so the derivative of x squared plus y squared with respect to x, and the derivative of 25 with respect to x. So the derivative of x squared is simple. There's no y's in there, so I just treat it, like any function of x, just the power rule. So 2x. Derivative of y squared, y is an unknown function of x, so I have to leave it as it is. I have to think of it as an inside function. So the derivative of y squared, first of all, the derivative of the outside would be 2 times y to the 2 minus 1, or 2y, times the derivative of the inside. Inside is y, so I just write it as dy dx. Equals the derivative of 25, the derivative of any constant we know is 0. Have a very simple algebra equation for dy dx, right? To solve this for dy dx, subtract 2x from both sides, divide by 2y, and I get dy dx equals minus x over y. So that's the derivative of y with respect to x for any values of x and y, any point on the curve. Now, they want you to find the slope of the circle at the point 3 minus 4. That just means you plug in 3 for x minus 4 for y, so I get minus x, which is 3, over y, which is minus 4. So I get 3/4. Okay? And then the last one, dy dx, if y squared equals x squared plus sine of xy. So I take the derivative of both sides with respect to x, right? Y squared equals x squared plus sine of xy is the derivative of y squared equals the derivative of x squared plus sine of xy. So the derivative of y squared, I got to use the chain rule. 2y times the derivative of the inside, which is dy dx. The derivative of x squared is 2x. The derivative of sine of xy, I have to use a chain rule now. I got multiple chain rule here, right? So I got to take the derivative of sine, which is cosine, leave the inside alone, xy, times the derivative of this inside, xy. But I have to think of the inside now as a product rule. First times the derivative of the second is x times dy dx, plus the second is y times the derivative of x, which is 1. I've done all the calculus, now it's algebra to solve for dy dx. So again, put all the dy dx's on the left side of the equation and factor out dy dx at the same time. So I have dy dx times 2y. Now I have x dy dx cosine xy, I bring over to this side. So I have minus x dy dx cosine of xy. Factor out the dy dx, I have minus x cosine of xy. All the terms that do not have dy dx in them leave on the right side, so I have 2x, and I have y times cosine of xy. Divide by what dy dx is multiplied by, and there is your derivative of y with respect to x, which of course has both y's and x's in it.